Welcome to Ask and Learn.
We are asked to prove Theorem 3 from the book. This theorem says, let C1, C2 through CK be real numbers, and suppose that the characteristic equation r to the k minus C1 r to the k minus 1 minus all the way down to minus CK equals 0 has k distinct roots, r1, r2, all the way through rk. Then we have that the sequence of complex numbers an is a solution of the recurrence relation an equals c1 an minus 1 plus c2 an minus 2 plus ck an minus k if and only if the sequence satisfies an equals alpha 1 times r1 to the n plus alpha 2 times r2 to the n all the way up to alpha k times rk to the n. For natural numbers n equals 0, 1, 2, and so on, and for some constants, alpha 1, alpha 2, alpha 3, and up to alpha k in the complex numbers. So first, suppose that this sequence is a solution. So we have that since the sequence is a solution, an is equal to alpha 1 r1 to the n, alpha 2 r2 to the n, all the way to alpha k rk to the n. And we have that r1, r2, and rk are roots of our characteristic equation. So that means that they satisfy r1 to the k is equal to c1 r1 to the k minus 1 plus c2 r1 to the k minus 2 all the way to ck. Likewise, r2 to the k is equal to c1 r2 to the k minus 1 plus c2 r2 to the k minus 2 all the way out to ck again. And we have that in general, this is true all the way up to rk to the kth power, which is equal to c1 rk to the k minus 1 plus c2 rk to the k minus 2 all the way out to ck. And now plugging in our sequence into the recurrence relation, we get c1 an minus 1 plus c2 an minus 2 all the way out to ck an minus k. This is equal to c1 times, and we have that an is going to be alpha 1 r1 to the n minus 1 all the way out to alpha k rk to the n minus k n minus 1, and this is going to be c1 plus C2 times alpha 1 R1 to the n minus 2 all the way out to alpha k Rk to the n minus 2, and so on, all the way down to Ck times alpha 1 times R1 to the n minus k, all the way out to alpha k times Rk to the n minus k, and this can be rewritten by grouping the terms with R1 together. So this is equal to factor out alpha 1 R1 to the n minus k you get that times C1 times R1 to the, and we have n minus 1 minus n minus k is k minus 1. And this goes all the way out to Ck plus factor out alpha 2 R2 to the n minus k. We get that times C1 R2 to the k minus 1 all the way out to Ck and extending this all the way, if we factor out alpha k Rk to the n minus k, we get times C1 Rk to the k minus 1 until we get all the way down to Ck. And we have, by our previous statements here, this is going to be equal to alpha 1 R1 to the n minus k times R1 to the k. This is going to be alpha 1 times R1 to the n plus alpha 2 times R2 to the n all the way out to alpha k times Rk to the n, which is an. And so we've shown that an satisfies the recurrence relation. So an is a solution. So we've proven the from left to right, or right to left, I mean. Now I want to prove from left to right. And to do this, suppose that an is a solution of the recurrence relation an equals c1 an minus 1 all the way out to ck an minus k, with initial conditions ai equals ci, where I ranges from 0 up to k minus 1. And we want to show that the sequence an defined by alpha 1 r1 to the n all the way out to alpha k rk to the n satisfies the initial conditions. So consider alpha n equals alpha 1 r1 to the n plus alpha k rk to the n. We have that the initial conditions C0, this is equal to A0, which is going to be alpha 1 plus out to alpha k, and we have that C1 is equal to A1, which is alpha 1 R1 plus out to alpha k rk, and likewise all the way down to ck minus 1, which is equal to alpha k minus ak minus 1, which is alpha 1 r1 to the k minus 1 plus all the way out to alpha k rk to the k minus 1. And so we have that the sequence an satisfies the initial conditions if the previous k equations here hold and a unique solution for C0 through ck minus 1 holds. But this is true since R1 through RK are distinct. It follows that a unique solution for C0 through ck minus 1 exists. And so we have that sequence an satisfies the initial conditions. And now we know that the sequence an, I suppose I should write this differently. This is the sequence alpha 1 r1 to the n plus alpha k rk to the n satisfies the initial conditions. And we know that both sequences are solutions since we proved in the first part that the second sequence is a solution, and both satisfy initial conditions. So both an and alpha 1 r1 to the n plus alpha k rk to the n are solutions and satisfy the same initial conditions. And we know that a linear homogeneous recurrence relation of degree k with k initial conditions has a unique solution And therefore, this unique solution is given by an equals alpha 1 r1 to the n plus alpha k rk to the n.